Welcome back again. So we viewed the overview of hypothesis testing, what the basic steps are. Now we're going to take a look at the specifics in doing hypothesis tests for a proportion. So we're testing a population proportion here to see if the sample supports any claims we've made about potential population proportions. So key concepts here. So we're going to describe the complete procedure for testing a proportion. And typically the basic statistics procedure is to use a normal approximation, which we'll look at the next slide here. We're going to look at doing the p-value method, and we're going to look at critical values, and we're going to mention the confidence interval method. Confidence interval method is actually slightly off, but it does still confirm in most cases our other methods. So we're going to use a normal approximation method just because it's more consistent with the method we're going to use for testing means. In practice, a lot of statisticians don't like that because there's a little bit of error in it. They prefer to use an exact method. We're not going to go over the exact method in this course. It's kind of a more advanced method using strict binomial probabilities. Can't use a critical value method, and that it's strictly a p-value test in that case. We're going to stick to the normal approximation in here. A note here of finding the number of successes. In many cases, you're given the sample size and then the sample proportion. Like here, they're saying we have a sample size of 926 users. 52% of them answered yes. Well, 52%, of course, is a proportion of p equals 0.52. But most of our technology that we would use to assist us in this requires a number of successes, an x value. So this is the total number of observation or the total sample size. Our number of successes has to be calculated. So we would take the sample size times that sample proportion of the 0.52, and as we would in most cases, we're going to get a decimal, 481.52. The technology that we're going to use in most cases, Excel won't accept a decimal. If you're using a TI-84 calculator, it won't accept a decimal. StatCrunch won't accept a decimal. We have to have a whole number because it's observations. You can't have a part of an observation. So this would be rounded up to 482. Now that might or may not be accurate. It could be 481 because we don't know where this percent was rounded. That might have been 51.5%. They got rounded up to 52%. Well, then the real number would have been 481 rather than 482. So there is a little bit of error that is introduced because of this. And that's what this is cautioning, is because of that calculation having to be rounded, there can be some error introduced into our test. So we're going to use the p-value method and the critical value method. I'm going to show you the confidence interval method here, but like we said, the confidence intervals are not totally precise because they don't quite match up with the percents of the confidence levels given. So recommended that you don't use a p-value, or it's recommended that you do not use a confidence interval to really perform a test. It's just if you want to estimate a proportion, use the confidence interval. When you go to test, use either the p-value or the critical value method. So let's test a claim about a population proportion. Our objective here is to conduct a formal hypothesis test about that value p. Some variables we're going to be looking at. We're going to be looking at n equals the size of our sample, which is also our number of trials or the number of observations. Then P is the portion of the population proportion. So it's the portion of the population that is successful or meets whatever condition it is that we're looking for. Remember, we're talking about a qualitative variable here, which is categorical. So we're looking for, does it have this property or does it not? So P is the proportion of the population that has that property. P hat, that little hat over the P is pronounced P hat, is the actual sample proportion. So it's the number of observations, successful observations in the sample divided by the total observations in the sample. Then, of course, Q is just the proportion of failures, so 1 minus P. So to test a claim, we have some requirements, the same as what we had for doing confidence intervals. We have to meet all the binomial conditions, so there has to be a fixed number of trials. That fixed number of trials is just our sample size. We're not going to keep gathering data until we hit, get some conclusion to work out. The trials are all independent, so each item is independent. Whether one item has the characteristic or not does not affect whether the next one does. There's two categories, success or failure. Success, either they have the characteristic, or failure, they do not have it. And that probability stays the same from one item to the next. And then finally, N times P. N is our sample size. P is the proportion of successes. Has to be at least 5. We have to have a big enough sample that we reasonably expect at least 5 successes. N times Q. Q is the proportion of failures. That has to be at least 5 as well. We have to have a big enough sample to expect at least 5 failures. And then, of course, that allows us then to approximate the binomial situation with a normal distribution so that we can perform our test. So our test statistic is going to be P hat, that's the sample proportion, minus P, which is our hypothesized population proportion, and then over that standard error, the square root of P times Q over N. So the normal approximation method, you could use XLStat, but like I said, my computer can't download XLStat because it's locked down by the school. You might be able to do it on yours. We will show you how to do it by hand and then how to use StatCrunch for it as well. We will also look at where do you find the standard normal tables. So an example claim here. The claim is most internet users utilize two-factor authentication to protect their online data. Most is saying more than 50%, or a proportion of more than 0.5. So greater than 0.5 is what that is telling us. Now, we had a sample of 926 users. We got 482 or 52% of them that said they did use two-factor authentication. Well, so you might be thinking, well, that's more than 50%, so doesn't that prove it? It does not. We could have just accidentally taken a sample that had more people in it than that used two-factor authentication than what is in the actual population. Remember, if we were accessing the whole population and surveyed them, and that came out to be 52%, that does prove it. But we're taking a sample, which is a small portion of the population, and it might not be perfectly representative of the population. So we're asking, is 52%, is that big enough that we can be confident that the sample having 52% means the population is going to be at least more than 50%? Well, that's what this whole process is all about. So let's go through the requirement check. There's 926 consumers. That is the sample selected, so that is our fixed number of trials. N times P, well, 926. P is our hypothesized proportion, which is at most means it's going to be 50% or 0.5. Well, so 926 times 0.5 is definitely bigger than 5. So we expect at least 5 successes. Q, remember Q is 1 minus P. Well, 1 minus 0.5 is also 0.5. So we're definitely going to expect more than 5 failures as well. So this is an example of output that would be given by XLStat, also pretty close to the same as what's going to be given by StatCrunch. You see here that gives the p-value. Now, alpha is what's called a critical p-value. If the p-value is less than alpha, we would reject the null hypothesis. So let me scroll down here. P-value is less than alpha means we reject the null hypothesis. If p-value is not less than alpha, we would fail to reject the null hypothesis. So now in this example, I haven't really stated what our percent we're testing at here. Let's go up and see if we said anything here. No, we didn't give a significance level in this test yet. So we don't really know what our alpha value is. Typically, alpha is going to be 0.05 is a pretty common one. That's not less than 0.05. So if that were the case, we would fail to reject the null hypothesis here. Now, we haven't set up our hypotheses yet at all, but this is just an example of the information given from technology, and we'll look at how to interpret that once we get to that point in the test. So an example claim, again, we're looking at the most internet users, so that is saying that the proportion is more than 0.5. The opposite of that would be less than or equal to 0.5. Remember, the one that contains the less than becomes the null hypothesis. So this is going to be the alternative hypothesis. And so right there shows us formulating those hypotheses, and this is what we're going to use to, to run our test. So we're using a level of significance of alpha of 0.05. So this is a 95% test. Again, if alpha is 0.05, then that output that we saw before of a p-value of 0.106, bigger than 0.05, so we failed to reject. But let's go through the process here of finding the p-value and everything from our data. So our test statistic, we have the p-hat. Remember, that is the sample proportion. That was the 482 divided by 926. Now, we know that came out to be 0.52. We were given the 52%. We like to put this fraction here just because it's more exact, because that 0.52 or 52% could have been rounded. So we tend to use that fraction instead to be more exact. Minus the hypothesized value. In the null hypothesis, the value was 0.5. So that's where that 0.5 comes from, is the value from the null hypothesis. So we subtract that to get a value on top. On bottom, we do that square root of p times q times n, or divided by n. And when we divide those values out, we get 1.25 is our test statistic. Well, we can either use a p-value test or we can compare that to a critical value. First here, we're going to look at the p-value. How do we find the p-value of this? Well, we're going to look at, since the alternative, H1, is greater than 0.5, the greater than, the inequality symbol is all we really care about here, the greater than. We are going to look at the right tail. What is greater than our test statistic? So our test statistic of 1.25 would be a z-score of 1.25 there. We want to know what's the probability and a standard normal probability of getting a value of z of greater than 1.25. Now we can use technology for this. My calculator will do it for us. If I wanted to use the calculator, if you happen to have a TI-84, you would go to second distributions, normal CDF, 1.25 to positive infinity. So 1.25 comma 1, 2, 3, 4, 5, 6 nines for positive infinity, comma standard deviation, or mean of 0, standard deviation of 1 is telling us that this is standard normal. That gives us a 0.1056 if we round to 4 decimal places. If you don't have the calculator, where can we find it? Well, let's go to, let's go to my math lab here. This is homework 10. Problem number 4 in homework 10 has these links to the z-score tables. This is the normal distribution tables that if you had a hard copy of the textbook, they would be in the textbook. Here we have to do the links. So you might want to write this down, week 10 homework, question number 4, so you know where you can access these tables if you need them. So we are looking at greater than, so we're looking at the 1.25 is positive. So we're going to look at the positive z-score table. So we want 1.2 right here on this axis, 1.2. We want the 0.05 up here. So that's right here. So it's this column, the 0.05, 1.2 is this right here. We get 0.8944. So the probability of z being greater than 1.25 is 0.8944. Now that z-score table gives us the probability of being less than or to the left. That's this probability. To get this probability, it's 1 minus 0.8944, which gives us 0.1056. Exactly what the calculator gave us, 0.1056. So that is our p-value, 0.1056. That is not less than alpha, so we would fail to reject the null hypothesis. What that means is we do not have enough evidence to reject the null hypothesis in support of the alternative. In other words, there's not enough evidence to support the claim that most users use two-factor authentication. Well, what if we wanted to use a critical value? So first, our Excel stat or StatCrunch is going to give us the critical value if we want it. The critical value here is 1.645. So we would reject, for using the critical value, we would reject the null hypothesis since, now for a critical value, it depends on the alternative hypothesis. Since the alternative hypothesis is greater than, we'll, come on now. Sorry, my screen's jumping all over on me. If the test statistic is greater than the critical value, we would reject the null hypothesis. Well, we've already concluded we're not going to reject, we failed to reject the null hypothesis. So we can see here, this is our observed value or our test statistic. This gives 1.249. We had 1.25 is where we rounded it. It is not greater than that critical value of 1.645. Therefore, we would fail to reject. The critical value method and the p-value method should always give you the same answer. So what if we don't have the technology? Well, we're looking at alpha of 0.05, and since the alternative hypothesis is greater than, that means we're looking at the right tail or the greater than side, we put 0.05 in there. Now again, our table gives us the left side of the probability. So 1 minus 0.05 would be 0.95. So we need to look up a z-score that is as close as possible, or sorry, a probability that is as close as possible to 0.95. The table goes to 4 decimals, so 0.9500, and look at the corresponding z-score. So looking at this table here, I have 0.9495 and 0.9505. 0.9500 is right between them. That's 1.6. This is 1.64. This is 1.65. So we go right between them, which is 1.645. And we'll go down here. You can see that actually on the table, they indicate 1.645 is what we use to indicate to a left tail area of 0.95, which is what we're looking for. So 1.645 is our critical value for this test. So that's where we get the 1.645. Our example claim here again, so going back to that two-factor authentication, because 1.25 is not greater than 1.645. Again, it's great. We have to be greater because the alternative hypothesis was greater. And since it's not, we failed to reject. So once again, we do not have enough evidence to support that claim that most users use two-factor authentication. So the confidence interval method. Now, like we said, the confidence interval method is a little sloppy. It's not always going to give us a result consistent with the p-value or critical value method. P-value and critical value method will always be the same as each other. The confidence interval is off by, and it's off by just, portions of a percent, but it's going to be enough that I don't recommend using it. But what it does, since this is a 0.5 significance level, and that 0.5 significance is in the right tail, or 0.05, I should say. Remember, a confidence level, the two tails have to be the same, so you put a 0.05 on the left tail, that leaves 0.90 or 90% in the middle. So it's a 90% confidence interval. If you go back to last week, we saw how to make a 90% confidence interval in StatCrunch for this information. Let's go ahead and do it again. So you go StatCrunch, StatCrunch website, open StatCrunch. A little tedious to get there, but that's okay. We go to stat, proportion stat, one sample with summary. 482 that used it out of 926. Now, this is a hypothesis. We did the hypothesis test here. I'll come back and show you that in a second. But let's do the confidence interval. A 95% confidence interval, standard walled, and we compute. And we get 0.4883 to 0.5527 if we round to 4 digits there. Well, what does that mean? Well, let's go back here. They get the same confidence interval we did. They rounded to only 3 digits. What that means, so if I'm looking at a number line, a continuum here, our 50% or proportion of 0.5 is right in the middle. Well, this goes, we said it was, 0.494 to 548. So what that means is our confidence interval goes from about here to somewhere in here. It contains values below the 0.5. In other words, it's possible that the actual proportion is down in here, that it's less than half. So this confirms our conclusion that we cannot definitively say that more than half or a majority of users use two-factor authentication. The only way we would have been able to confirm it is if our confidence interval was completely greater than 0.5. If our confidence interval looked like this, then we could say, hey, there's very, very little chance that the true value is less than 0.5. So then we would have said, hey, this does support the claim that it's a majority that use it. But this is the case that we had. There were values less than 0.5, so it's possible that it is not a majority. Let's look at another example here. So our example here, we want to say that fewer than 30% of adults have sleepwalked. And our evidence here, our sample, in a sample of 19,136 Americans, only 29.2 have sleepwalked. Now you might say, well, that's really close to 30, but this is a really huge sample. So is the 29.2, is that small enough to say that we're pretty confident that the number for everybody is less than 30%? Well, let's go through the process. We're going to use a 0.05 significance level, just because that's standard. And we're testing that the population proportion is less than 0.03. So let's go through the requirements. This is a simple random sample because we have a set sample size of 19,136. This is a fixed number of trials. I'm pretty sure that gives us at least 5 successes and 5 failures with 19,000 sample size. 0.3 actually gives us close to 6,000 expected successes. So we're safe there. Our original claim in symbolic form, less than 30%, is P is less than 0.3. So the opposite would be P is greater than 0.3, giving us our hypotheses here. Remember, greater than or equal to, the equal to goes with the null hypothesis. Now that says strictly equal to, but remember we know that really means greater than or equal to because the alternative is less than. We just always word it as equal to because that's creating that hypothetical sampling distribution. So let's go ahead and do the claim. We've got our significance level. Because this claim involves a proportion, we can use that normal distribution, that normal approximation. Here's our test statistic. So the 29.2 is 0.292 minus, remember that 0.3 is from the null hypothesis, divided by, we use the 0.3 as our P, 1 minus 0.3 gives us 0.7 for Q. So we get a test statistic of a negative 2.41. Well, what was our critical value? Well, let's find it. Here, the alternative is less than. So that means, looking on the significance, alpha of 0.05 is on the left tail. So we want to find 0.05 and get that value. So we would look in the negative z-score tables if we were looking here. So let's go back to assignments. In homework 10, I can find my tables. In problem number 4 again, I want the negative z-scores now because I'm on the smaller end. So I want to find 0.050 here, or as close to it as I can get. I see I have 0.0505 and 0.0495. I'm exactly between it. So again, that gives me negative 1.645 is the critical value for that. So they put that down at the bottom of that table for us as well. So my critical value is a negative 1.645. And since the alternative hypothesis is less than, we have to have a test statistic less than negative 1.645. Well, our test statistic of negative 2.41 is less than negative 1.645. So this is telling us we have sufficient evidence to reject the null hypothesis in favor of that alternative. So yes, it is fair to say there's evidence to support that less than 30% of people have sleepwalked. If we wanted to use the p-value method, well, then we would go and find the excuse me, we would find the p-value probability that the z-score. Now remember, alternative is less than, so we're looking at less than negative 2.41. Probability being less than negative 2.41, if we go to that table, it gets to be, I believe it's like 0.0080 if we look it up. Again, on that table, let's go to it again, why not? So again, it's a negative number, so we're going to go to the negative table. So that's the first one. And it's negative 2.41. So we want negative 2.4 over here. That's right there. And this is the 0.01 column for the third digit. So 2.41 is right here, 0.0080, exactly as we saw. So our p-value of 0.0080 is less than alpha of 0.05. So again, that confirms that we reject. If we wanted to use technology, we'd get an output similar to this. This is telling us we have the critical value, and the observed value is our test statistic. And it gives us our p-value down here and alpha. So we can see here that we definitely have, the difference really is not meaningful here. For our methods here. The difference is for other tests. So now let's go to StatCrunch and take a look at running this in StatCrunch then. We did the confidence interval. Let's do the actual test itself. In fact, let's go back and let's do this one first. So we're using summary statistics. Now we need the number of successes. We had a sample size. Let's go up here of, where was it? 19,132 and a proportion of 29.2. So let's go to my calculator. I'm going to go to this is just using this as a regular calculator here. 19,136 times 0.292 gives us 5,587.7. So we're going to have to round that up to 5,588 successes. So in StatCrunch, we do 5,588 successes out of 1,000 or 19,000. Got to grab that number again. 136. And this is a hypothesis test. The alternative is less than. The number is 30% or 0.3. Now I'm going to have us get to show the critical value. Make sure you remember to check that box down there for critical value and put in the level of significance, 0.05. Hit compute, and there it is. So there is our test statistic, negative 2.41, our critical value, and our p-value. It doesn't list alpha here, but we selected our alpha. We know it's 0.05. So this confirms all the information that we had there before. So that is running a hypothesis test with StatCrunch or doing it by hand using those probability tables. If you have any questions, please let me know. Otherwise, we'll move on here in the next set. We'll look at tests for means.